Sadia.
All right, so we are live now. Assalamu alaikum, everyone who's tuned in, everyone who's joined us at Zoom, and everyone who's tuned in to Facebook Live as well. Welcome to another edition of the Women Engineers Pakistan webinar series. This particular webinar, the July one, is brought to you in collaboration with the very amazing Women in Energy, and we have Ms. Sadia Qayyum from Women in Energy, who will be speaking very shortly and will be introducing the webinar and our very esteemed speaker today as well. Sadia, you want to go ahead and tell us a little bit more about Women in Energy, please?
Yeah, sure. Thank you, Ramla. And we're very excited to be hosting this webinar, second webinar of a joint webinar series that we launched with Women Engineers Network back in January. And today I'm excited, particularly because of the topic and because of the speaker, Dr. Afreen Siddiqi. Before I go on to talk about Dr. Afreen and the topic that we have, let me briefly talk about Women in Energy. So this is a professional network that we started in 2018. It's a network of female professionals in the energy sector. And our members include not just engineers, but also non-engineers, such as economists, we have lawyers, we have architects, we have urban planners, and finance experts. And these women are working in not just renewable and non-renewable energy projects, but they're also in the public sector and private sector. And something that we take pride in, that our members are fresh graduates from university, who are seeking jobs in the energy sector, and also women who are leading the respective companies, organizations, and their departments and their organizations. And we've done a number of activities like webinars, which we have and site visits. And if you want to learn more about Women Energy, please tune in. Please connect with our LinkedIn group, our Twitter group, and Twitter and our Facebook group. Oh, now talking about the water and energy nexus. Sorry, if you can hear that disturbance, that's my son. Let's open him in. Azan, say hi to everyone. He is our future energy expert and male champion. So water and energy nexus, we know in context of Pakistan, it's extremely important because Pakistan is a water-stressed country. Prime Minister Imran Khan has repeatedly talked about how Pakistan needs to improve or use more water more efficiently, and we need to increase our water capacity. As the population grows, as there's economic development, as we add more generation capacity, this interlinkage between energy and water becomes more important, because we use water to produce electricity through hydropower, and we're pumping water and using electricity to pump water. Now talking about our speaker, who we're very excited to host, Dr. Afreen Siddiqi. She's a research scientist at MIT. She's also adjunct faculty at Harvard Kennedy School, and I met her while I was at HKS while I was there. She has numerous publications to her credit. And she's been published in leading journals like Energy Policy, PLOS One, Current Opinion, Environment, Sustainability. She's done her bachelor's, her master's, and her numerous awards to her credit as well. And she's won the Amelia Earhart Fellowship, Richard DuPont Fellowship, as well as the Miller Prize. Sorry, my son is a big disturbance right now, so I'm going to over to you, Dr. Siddiqi.
Great, thank you. Thank you so much, Sadia. Thank you so much, Ramla. It's a real pleasure to be here, and I really want to thank you all for organizing this. I was delighted to hear and excited to hear about everything that both of your respective groups are doing, Women Engineers Pakistan, Women in Energy, and it's really exciting to be part of this. So we hope for something that grows in the future and sort of becomes an important influential sort of platform to inform both engineering as well as particular activities in energy. And I also want to give out a special thanks to Professor Sarah Jordan, who connected me to this group, and it was really great. So today I'll be talking about the water and energy nexus in Pakistan. And this is an area that I've been focusing on in terms of research for a few number of years. Let me see if I can quickly share my screen. Okay, so let me bring this on. Now, is this visible to everybody?
Yeah.
Okay, great. So I will give a very quick, brief background of my academic preparation so you can sort of see the angle at which I'm looking at this problem. My professional and academic background is in engineering. So I have a bachelor's in mechanical engineering from MIT, a master's in aeronautics and astronautics, also from MIT, and a PhD in aerospace systems from MIT. So I'm deeply entrenched in the engineering design, in the engineering discipline. And in terms of my professional practice, I worked as an engineer at National Instruments in Austin for a few years until I really found my calling in research. So currently I'm a research scientist at MIT and also an adjunct lecturer at Harvard Kennedy School. I focus on a number of different areas, but the overarching theme in my work is doing systems analysis that can inform policy, planning, and design for technical systems that are facing future uncertainties. Among the different types of work and areas that I focus on, energy and water is a major one. This is sort of a word cloud to give you a sense of the work that I've been doing the past few years. So word cloud of my recent publications, and this will just give you the overall message that I have a strong focus on looking at energy issues, water issues, and I use data, systems analysis, and so forth to look at questions that are relevant for both planning, policy, and design. So in the context of the nexus of water and energy, and particularly for Pakistan's case, I wanted to sort of take this opportunity to first both introduce what is this issue of the water energy nexus and how does it pertain or apply to Pakistan. So many of you might already be familiar with this, and for those of you who are not, this will serve as a brief introduction. So when we say the term the water energy nexus, this is sort of a not just a buzzword, but a real concern that sort of started catching traction both in the academic community as well as in the practitioners community almost about a decade ago. And the main issue is that the constitutive processes in both water and energy systems are recognized to be resource linked. So if you look at the modern systems that provide water to us, there's a process of abstraction where water is obtained either from the ground or from the surface, and that typically requires pumping. Then the water is sort of purified, it's treated for use, whether if we're getting it from the sea, then it's desalinated. If we're getting it from other sources, it goes through various proper treatment. Then it is conveyed through urban networks or long distance pipelines. Eventually it is used within residences, within homes, within industry, and then hopefully it is treated before it is disposed back to the environment. And then in the energy sort of cycle, there are three key sectors or three key processes. One is of extraction, where the natural resources are extracted, such as coal or oil, even uranium for nuclear power. And then the fuel is processed. So the coal will go through different types of processing before it can be used during the mining process. Oil refinery processes and so forth. And then ultimately, the fuel might be used in power plants to turn steam turbines or in nuclear power plants and so forth to generate electricity. Now, historically, these sectors of water and energy, they have really focused on their own particular processes and their own particular domains. But what has become increasingly obvious is that this historical siloed sort of consideration is not feasible for the future. In reality, what really goes on is that a significant amount of water is used for resource extraction. When we're talking about coal mining, actually, it levies quite a bit of demands on water resources. Because water is used to basically turn a number of mining processes, particularly slurry and so forth, for transporting coal and so forth, and particularly as well as for oil production. A lot of water is injected within the oil wells for production. And then, I can sort of go on. I'm not going to describe each of these in detail, but these arrows will tell you that there's a lot of linkages. So water is used for fuel processing, water is used for electricity generation, and then vice versa. Electricity is really used for pumping a number of processes that take place within the water value chain. And both electricity as well as diesel fuel are used. So you can now see that, these two resources are actually interconnected, and this interconnection needs to be recognized, particularly for the future where the demands for energy and water are both rising, and water is a constrained resource, and population is rising, so which is leading to the increase in demand. And if we don't account for these interlinkages, then it may very well be that we may institute solutions or institute systems that impose greater demands on another linked sector, which have not been adequately accounted for. So you may create solutions in one sector, but create problems in another sector, and vice versa. So this integrated thinking is very important, and this integration of these or interlinkages is what we call the water energy nexus. A lot of these issues were highlighted almost a decade ago, as I said, in World Economic Energy Forum meetings. There was a survey that was done for electric power producers, the CEOs of electric companies in 2008, and they were asked to where they would, rank issues of water, and you see the red dot in 2008 survey, and they sort of put it in the green zone. And then a year later, the survey was conducted, and the issue had been highlighted so much and had caused enough concern that the water highlighted again in the red dot here was put in the yellow zone, and it has sort of stayed that way since. It has been recognized that this issue is not something that can be sort of discounted easily. And one of the reasons why the water issue was highlighted in the energy sector was the number of heat waves, forced plant closures, and temporary sort of halt and curtailment of power plants because of the thermal loading that was happening in rivers and waterways that were being used for cooling these thermal power plants. So just to back up, as I mentioned earlier, water is used in electricity generation, and it is used in two important ways. It is used for cooling operations and thermal power plants. So as thermal power plants, although they're burning fuel, they basically need water to complete the generation cycle because it is used in an important cooling process, which is part of the generation cycle. The more efficiently a plant can cool, the more efficiently it can produce power. So it has a direct bearing on the amount of electricity a power plant can produce and the cost of that production of that electricity. And if the incoming water, which is supposed to be used for cooling, is too hot, then it will affect the efficiency of the thermal power plant, and it will affect the amount of electricity that can be generated. And if it gets too hot, then at a certain point in time, you cannot discharge, hot water back into the environment because there are environmental constraints in many regions around the world. So in countries such as France, and particularly in many even locations in the US, power production had to be curtailed because of the very high temperatures that occurred during heat waves and really affected electricity generation. And that served as a wake-up call for power producers who realized that we cannot take water resources and their availability and their state for granted. And one needs to understand how might the availability of water in the future affect power generation, where it may very well be that the supplies of water itself might be lower, so there's just not enough inflows to begin with in the rivers and streams, or the water may just be hotter because of climate change and because of heat waves and so on and so forth. And that also would affect power generation. If you look at the water intensity of electricity generation, here's a little chart that will show you that depending on technology, the water demands can vary significantly. So on the can you see my cursor that I'm pointing at? Is the cursor visible? Okay. So you can see that some of the renewables, the water demands are minimal, right? So for wind power and solar PV, there's not much water that's needed. But if we're operating steam turbines, then water is needed again for the cooling operations, as well as there's some evaporation as well, right? Similarly, water is used in nuclear power. Again, most of the use is for cooling operations, as well as, if you talk about carbon sequestration and storage, advanced coal with CCS, again, water needs are great. And if you appreciate that, the numbers down here are showing water consumption per megawatt hours of electricity generated, you can appreciate the great variation that exists based on technology of the energy generation. So what this indicates is that if we don't account this in energy policy, then we are neglecting an important resource, which is water, and subjecting the system to future uncertainties of water availability that could be critical in affecting the economics of the project, in affecting the productivity of the system, or even creating risks that perhaps could be avoided if better planning and consideration is done. Similarly, if we go upstream, if we just even look at fuel production, so looking at oil production or coal, and even corn ethanol and biofuels was a great interest in many regions. Again, you can see the water needs, and if you'll appreciate, this is a log scale here on the x-axis. So these numbers get large very quickly as we move to the right, and you can appreciate that certainly corn ethanol, cellulosic ethanol impose great water penalties, but significant water is needed for oil production and enhanced oil recovery operations, EOR, where where water is used for injecting and creating additional pressure to recover additional oil. So water is an important resource when it comes either for producing oil and coal all the way to electricity generation. And essentially the main message is that energy policy should factor in these water use implications, and particularly recognizing that although historically a region may not have been water scarce, or historically water may not have been an important issue to consider, but going out into the future where we do know that scarcity is increasing, we need to account for it. And now similarly on the other side, if you look at the energy intensity for water, we have a similar situation where, as I mentioned earlier, energy is needed to abstract water from sources, to convey it, for use, to treat it, to distribute it, to dispose it. And depending on the different processes that are used, the energy consumption can vary significantly. When water is abstracted from surface sources, this is taking it from a river or from a lake, there's some kind of pumping involved. From when it's abstracted from the sea for desalination, again, significant pumping is involved. But typically when it's extracted from the ground, the energy intensity on a relative basis is typically higher. Now, these are just average values. They can vary greatly depending on the region and depending on the location. But this is just to give you a sense of the scale involved and a relative sense involved of the energy consumption as it relates to different processes for obtaining and using water. I'll come back to this issue of the high energy intensity of groundwater later today, but I just want to point this out here as we are comparing the energy intensity for water and water intensity for energy. Okay, so this is just to give you, I hope this gave you a bit of a background on how water and energy are linked and why it's important to consider them in an integrated way as we plan both for water resources as well as for energy production into the future. So in Pakistan's context, there are a number of key and important issues that are relevant in the water energy nexus, and I'm going to highlight two of them. The first one I'll start with is, of course, hydropower. Right, this is a major part of the energy portfolio, and many people are certainly intimately aware, but let me just give you a very quick snapshot of where the hydropower connection comes from. So if you look at the Indus River, it starts mountains in Tibet, and I'm always intrigued every time I look at this map that the Indus River actually flows sort of westward for a long period of time until it just sort of makes a very sharp turn, enters through the length of Pakistan and meets the Arabian Sea after sort of covering a distance of relatively short distance of 3,000 kilometers. So it's literally starting from, as they say, right, the roof of the world, right, Tibet, some of the highest altitudes that we will find, and then meeting the sea, which is sea level, in a relatively short distance. And what that then means is that it has tremendous hydropower potential, right? It goes through tremendous change in potential energy as it is climbing down from literally the maximum heights that exist on our planet to sea level. Secondly, it is also carrying a large amount of water. So if you actually look at the average discharge of the Indus, it is significant. If you compare it to many other major rivers of the world, you'll appreciate that it's actually carrying tremendous volume of water. If you compare it with the Nile, the average discharge of the Indus is twice that of the Nile. So this is something that we actually don't appreciate, and we sort of, the issue of scarcity and the issue of, a lack of water is often highlighted. But in my view, what also needs to be understood is that there is actually quite a bit of water that the Indus and its tributaries are providing, and the water that is flowing through the territory of Pakistan, which needs to be understood as such, because when you compare it with many other regions of the world, I would argue that this water resources is still sufficient to meet, the needs both for consumption as well as for energy generation, if it is harnessed wisely, if it is used efficiently, if it is built with strategic insight, both for environmental concern as well as for concern for economic development. Okay, so with this little bit of background, the Indus has been developed for a number of hydropower projects, and it continues to host a large, significant, untapped hydropower potential, and there has been tremendous investment and activity in building hydropower plants. But what needs to be understood, and I'm just going to highlight, sort of key issues as they relate to the water energy nexus here, is that as hydropower systems are built, these systems is what we call in long-lived infrastructure. They are supposed to operate for decades out into the future. And it's precisely those decades out into the future that are going to be highly uncertain when it comes to water flows. There is still not a clear picture of what the flows may look like 30 years from now, 40 years from now, 50 years from now, when some of these plants should be able to operate. Or often they are, evaluated for decadal performance and decadal returns on investment. So out into those future decades, it is very unclear what the flows may look like, particularly if you recognize what the flows of the Indus comprise of. It actually, if you compare it with other rivers in the basin, a large fraction of the Indus flows basically comes from the snow and glacier upstream discharge. So this NMI, normalized melt index, NMI, basically shows you the fraction of the flow, which shows the breakdown of the flow based of snow melt from snows and glaciers, and the contribution across the different rivers. And you can sort of see that the Indus sort of stands out in terms of its dependence on snow and glacier discharge as compared to the other rivers. And what that then also means is that if there is upstream change, as being recorded and observed, the change in the Indus flows is also going to be an important thing to consider. And here's a picture on the right-hand side that you're seeing a plot from John Briscoe's sort of report that was done, again, almost a decade ago. But I don't want to dwell on these particular numbers and on these particular values, but I do want to point the overall picture, what these graphs are painting, which is what this picture is showing is that out into the future, so this is, 10 years out, 20 years out, 30, 40, 50 years out. So they're looking at decades out into the future and looking at different possibilities of percent change in the flows, depending on how much warming that may or may not occur. So again, these are all projections, and no one can say for sure what they may look like, but certainly you can appreciate that if any of these projections were to pan out, what they're really showing is that further out into the future, the percent change is all negative. The expected flows are expected essentially eventually to decline, and in some cases very significantly, right? 20% decline, 30% decline, 40% decline, even in some cases projecting, a century from now, 70% decline. Are the systems that are being designed capable of responding to this change? And can they deliver value if these changes were to occur more rapidly? As you can see, this is a century out. So, 10 decades out into the future, we're talking 100 years from now. And this data is 50 years from now. But sometimes change can happen much more rapidly. So I just want to sort of illustrate that as studies are being done and as hydrologists, glaciologists, and experts are looking at this question of flows, there's just significant uncertainty in what the future flows will look like for the Indus and its tributaries. And this needs to be understood and appreciated. Okay, trying to move my screen, but okay. So, and if you look at, even existing systems that exist in the Indus, such as the Terbela power station, where, arguably, climate change was less of an issue, the flows were more predictable. If you look at the actual generation that has transpired, it was much more variable than what was actually expected. And you can, so I've plotted, the average generation at the minimum and maximum levels, and you can appreciate how different they are, especially so this is for the case when, supposedly the flows are more predictable, supposedly there was better data, so on and so forth. So what might the future hold for new systems where there's still a lot of uncertainty? So I really want to, hammer on this point of uncertainty. And currently the regime of the inflows into the system is this blue line that I've plotted here, million acre feet. This is the cumulative probability distribution based on the previous hydrological record that currently exists. But how this hydrological record will change in the future is anybody's guess. The expectation is that the flows eventually will increase and then they will decline. Depending on where this curve shifts, whether there's more flow or less flow, there are impacts and implications for how projects should be designed. One key thing that I want to highlight as hydropower systems are sort of designed and planned in Pakistan is that there's a significant amount of focus on the capacity numbers. So, project with, this capacity. And they really talk about, megawatts. But what really should be a point of discussion is how much energy can eventually be generated. And it's not just about how much megawatt or the potential capacity that a project has, but how much flow that one might expect through it, and therefore what the capacity factor would be, and therefore the resulting energy would be. So we can have a very large plant, but if there's not enough flow, then the energy generation is going to be very different. So understanding the energy generation is critical, but I don't see enough emphasis of this. And most of the projects are simply evaluated based on megawatts alone. And depending on the same project, as I've highlighted here, right? So this is a log scale. So as we go on the y-axis, these numbers change very quickly. Some of these projects have the same exact capacity, but we can see very different mean energy generation. So therefore, this is something that really needs to be understood and something that needs to be properly accounted for when projects are being funded, when projects are being evaluated, when projects are being sanctioned. Okay, so when we look at the overall portfolio, I want to show that, there's great distribution that exists. There are some projects. So what I've plotted here is, the number of projects. This is based on data which was provided by PPIB, Private Power Infrastructure Board. There was a report that was published in 2004, which gave a very detailed list of potential projects, some of them which have been built and many of them have yet to be built. And I've sort of sorted that data out and showing the distribution that in terms of megawatts, here are some very large projects, right, on the order of thousands of megawatts, all the way to smaller projects, and how many there are. So this is what we call, the large hydro, so systems that can generate greater than 50 megawatts of power. But then you can see that there are many, many, many projects that are actually kind of small, and there are the different terminologies that are used: small hydro, mini hydro, and micro hydro, which is used in the sector. And it would be very interesting to strategically consider these small projects, because while some of these very large projects would be subject to the uncertainties that I was mentioning about future flows and how much energy can actually be generated from these systems, these small projects might be very interesting ones to consider given their distribution in the country. Many of these small projects are actually further downstream. And the marginal impact these small projects might be able to bring to local communities that are energy deprived. So I will talk about this a little bit more. Excuse me. In the interest of time, I'm just going to say that while there's significant interest, of course, for energy security in looking at the large hydro projects that exist in the northern parts of the country, if we go further downstream of the Indus Plain, the potential, of course, decreases, but there's still enough interesting sites that can generate electricity. And if you look at the distribution of those sites around the country or through the country, one can then start imagining what marginal impacts these smaller projects can bring to the communities that have to pay for expensive electric power that is being generated through either thermal power plants, or have to create power by burning diesel or other fossil fuels, which are arguably more expensive. So if we start considering all of these other options, as well as perhaps, greater uncertainty that some of the larger projects will be subjected to, but perhaps maybe the smaller ones may not. All of this needs to be strategically understood and considered as we think about how water and energy are interlinked, and how can we create strategic plans and new systems that can help us address at least some of these issues in a more in a smarter way. So I'm going to sort of skip through this, and some of the diagrams that I was showing, some of the figures and results I was showing, they're summarized in some work that we published a few years ago, in which we did a very detailed assessment of the hydropower portfolio from a variety of different perspectives, looking at the environmental issue, looking at the distribution issue, and so forth. So anybody who's interested is welcome to review this. So this is, was one main point I wanted to make on hydropower systems, and particularly the uncertainty in flows, as well as the distribution of potential hydropower systems throughout the country. And how that distribution can be interesting if you think about energy supply and its distribution around the country. Looking at the other coin, other side of the coin of this water energy nexus, I'm going to talk about groundwater pumping, right, where we use energy to basically extract water and use water. So if you look at the Indus Basin, I really like this picture. This was drawn by the Food and Agriculture Organization, FAO, where they show basically percentage of irrigated land as, as a percentage of area. And you can see this big, long red zone here. A large part of this is Pakistan. Of course, it's Northwest India and Pakistan here. So if you compare it with the global map, you'll appreciate how intensively irrigated our country is, and how it compares to the rest of the world. It's a large section, which is primarily, Punjab here, which is intensely irrigated, and it actually stands out in terms of irrigation intensity, in terms of the contiguous area that is irrigated when we compare it to other major regions. Here's the Nile Delta, here's the Mekong Delta, here's the Central Valley in California, so on and so forth. So you can appreciate this vast area that actually really stands out globally in terms of the intensity and extensivity of irrigation that occurs here. And how is this irrigation happening? Well, it is happening through a network of surface canals that have been built over almost 2 centuries, and serve to irrigate tens of millions of acres, contiguous acres in the country. But what has also happened is, so here's a nice picture actually that I wanted to share. This was taken by Professor James Westcote. So here's a picture of Punjab. You can see, the vast agricultural land, all of it really, being able to do agriculture because of irrigation supplies. Otherwise, the region is arid. The rainfall in Pakistan is very minimal. But if you look at the surface irrigation system, the canal withdrawals actually over time have been declining. So you can see these negative numbers here. I've just plotted, sort of just the average trend over time. And you can see that the total, withdrawal over time has been declining over the past decades. So how has agriculture been able to keep up when water withdrawals through the canal system has actually not increased, but actually has decreased overall? Well, it has kept up through groundwater pumping. Here's a plot that we made of tube wells that were reported for different districts in Punjab in 1995, and here it is for 2010. And if I were to show it to you for 2015, you will see even more. So the number of tube wells has risen exponentially. And I'm showing Punjab here because here's, where the major agricultural production is happening. Certainly, Sindh has significant amount of production as well, but I'm just showing Punjab because that's where I was able to get to the data most easily and over a long time series. And you can see the number of tube wells that are reported. So this is data coming from Punjab Development Statistics. So this is officially reported data, and you can appreciate this growth in groundwater pumps over decades. What you can also appreciate is that the red bar shows groundwater pumps that are using electricity and groundwater pumps that are running on diesel. That's the gray bar. So the majority of the groundwater pumping is happening using diesel. It's not happening from the electric power system. And why is it diesel? Because you don't need electricity connection. It's much more portable. It's easy, so on and so forth. But if you look at this report number of tube wells in Punjab, which you can appreciate certainly that has grown, and if you look at the energy use, the picture didn't add up. This is the reported energy use, the officially reported energy use in the energy yearbook. And what you can see is the red bar, which is electricity sold to the agricultural sector. And the gray bar is showing the light diesel oil consumed in the agricultural sector. And this picture showed that the diesel-based pumping was increasing. And this picture shows that the diesel use has declined. So certainly something was not adding up, because my expectation was we started doing this project because we wanted to quantify how much energy was being used for pumping and how much energy was being used in the agricultural sector. But when we looked at the reported data, it just didn't add up, because we can see that the diesel use is reported to be declining over time, but clearly year after year, the diesel-based pumping has been rising. So how can this be? So it turns out that, so we decided to do our own analysis, and we built a simple model, at the farm level. So, the machinery that is being used, different types of tractors, tube wells, and the different types of fuel that is being used, high-speed diesel, light diesel oil, and electricity. And we mapped out the different operations that it was being used for. And then we essentially collected data from Punjab, from the Pakistan's agricultural machinery census, which is done on a 10-year basis. So we got the census for 1994 and 2004. And that census provides incredible amount of information for, the type of machinery that is being used. And based on that census, what we found, and then our basic, sort of calculations that we used, what we found was that indeed, LDO use has been declining. Light diesel oil use has been going down. The tube wells are not operating light diesel oil. This is the actual reported data, and the red line is showing our own calculations just based on our model. And you can see that, our model was able to calculate it relatively well. What has happened is that a lot of the pumping is now happening through high-speed diesel, which is simply not reported in the energy yearbook. So what is happening is there has been a shift of fuel type from light diesel oil to high-speed diesel for groundwater pumping in the agricultural sector. But what continues to be happening is that the high-speed diesel oil is simply just not reported for agriculture. And that is why we see a declining use of energy in the official numbers, which is only reporting LDO, and HSD is simply not reported for agriculture. So based on our own calculations, what we find is that if we end up including this HSD, this high-speed diesel, which we were able to do using the machinery census data, which showed us which were the pumps that were using HSD, and then that's how we made our calculations, you can actually see that, the energy for pumping has risen significantly over time. And some of these jumps that you're seeing are actually the drought years, when a significant number of additional pumps were added onto the system. And although field operations, this is for tractors and so forth, they're ongoing, but pumping constitutes a significant use of energy, and that's the connection. How much energy is being used just to abstract water for irrigation. So based on our calculations, what we found was that water pumping in 2010 constituted about 12% of total energy use in Punjab. This is significant. And farm operations with tractors, about 8% of total energy use. The official numbers are based on our calculations. This is the breakdown of energy consumption in Punjab, where we estimate that it is up to 20%. So 20% of the energy use in primary energy use in the province, we estimated was going in agriculture, which in some sense is not surprising. Punjab is a big agricultural province. But if you look at the officially reported data, it says only 3% goes into agriculture. So what is right? What is not right? The issue seems to be of bookkeeping. As I mentioned earlier, that light diesel oil is reported for agricultural use. And if you only look at light diesel oil, then indeed, agriculture doesn't account for a whole lot of primary energy use. All of that HSD, the high-speed diesel, is bookkept in the transportation sector. So you can see the transportation sector has a significant pie. But if we were to basically carve that pie out in a different way and attribute that high-speed diesel to agriculture, which we are doing just based on the machinery census numbers, then agricultural share will increase, transportation share will decline. Now, this is just an estimate. For a better, estimate, what will really be needed is some field testing and field data, which is specifically collected for this particular question. But what we wanted to highlight through our study was that there is significant knowledge gaps that exist currently. There is significant issues in how data is being reported currently. It's a matter of bookkeeping. So high-speed diesel, of course, is reported, but it is being bookkept in the transportation sector. Whereas what we found was that based on the machinery census, certainly a lot of diesel groundwater pumps are using HSD, and when you start accounting for that, agricultural share for energy increases. So there's something that needs to be sort of fixed here, both in terms of data reporting as well as updating and getting a true picture of what is the energy consumption for water. And our estimates show that it is far greater than the reported 3% for sure. And this is something that really needs to be understood and needs to be looked at in more detail to get a more proper accounting, because again, these are just estimates based on the quality or based on the best data we could find, but better measurement and better data collection can help really resolve where the situation stands currently. Certainly it is more than 3%, and whatever that is, that needs to be understood, because what that means is that a significant amount of energy gets used for only abstracting water for agriculture. Now, if we were to use our estimates based on, the model that we had and the data, what we find is that the direct energy use in agriculture has risen 1.5 times in Punjab. So in order to produce, the same amount of output, we are putting in more energy. So to give you a sense, this is a very gross measure, but if we just look at agricultural production, right, the direct energy intensity has increased from 1 megajoules per kilogram to 1.86 megajoules per kilogram. So to produce the same kilogram of output, we have to put in more energy. A lot of it is driven by groundwater pumping, because we have to mobilize all this water from the ground to bring it up to create, the production levels that we're seeing. So, this has grave implications. This needs to be understood and appreciated. How much pumping is sort of impacting the energy use for agricultural production. Okay, so a lot of these results and the details of the model and so on and so forth were provided in a paper that we published in 2013. So for those who are interested, you can take a look, and all the data sources which are derived from officially reported data are also referenced in that paper for those who are interested. So how do we, sort of address this issue? As I mentioned, groundwater pumping is, related to a significant amount of energy use. One common response or one common approach is looking at solar power pumping, where the idea is, well, instead of consuming diesel, we can use solar power pumps. To some degree, that is possible, but solar power pumps continue to be fairly expensive. And secondly, what they also do is that they can lead to other issues, such as people pumping indiscriminately and creating further over abstraction of the groundwater resource, and so on and so forth. So solar power pumping is not a silver bullet. It has its own issues, both in terms of cost as well as potential pitfalls of over abstracting the groundwater resource, because now there's no cost for energy, so people will pump even more, and that can create unintended consequences. Here's another situation, or here's another solution that might be interesting to consider for Pakistan, which is coming back to this issue of small hydropower, where small hydropower systems, perhaps in the canals and waterways, can be used to provide electricity, both for limited groundwater pumping as well as other agricultural uses in the rural areas. So this again connects our water and energy system. This again connects our question of water and energy planning in an intimate way. But this is something very real for Pakistan, because where there's a very extensive network of canals, some of these canals are almost as big as rivers in their own right. There's a tremendous amount of water that's flowing through these canals. Can these canals be harnessed for not only delivering water on the surface, but also generating small amount of hydropower that can then be sort of distributed locally and used for agricultural operations? So this would reduce the diesel consumption. This would create cheaper energy that can be used, more clean energy, as well as create or provide energy where perhaps there's just not enough electricity to begin with. So this is an area that can certainly be looked at in detail in Pakistan. It may not be possible for all types of channels. So some of the channels are very small, and it will impact, the flow distribution, of course, because as we extract out energy from the flowing water, it will impact, distribution and so forth. But this is something that can be studied. There's certainly plenty of large channels that can potentially be analyzed. So here's some early work that we started looking at, energy generation potential on major canals in Pakistan. And you can see, some of the canals that are plotted here just by an index, and the megawatts of capacity in terms of, different sites that exist on these canals, on which, small hydropower systems can be potentially be installed. Here's a picture of an in-stream turbine. So these are special types of turbines that harness flowing water. So they are not the regular types of turbines that require, water to be falling from a significant amount of height, but rather they harness the kinetic energy of flowing water. So they're all different types of, all kinds of different types of turbines and technologies that are now available that can be considered for use in small-scale hydropower production in the different waterways in Pakistan. So with this, I will sort of wrap up. And I just want to sort of, highlight some key takeaways. One is that, I didn't really call it the water energy food nexus. Some people do it in Pakistan. It really is the water energy food nexus, because most of the water that we're talking about is really used for agriculture. But nonetheless, both water, energy, as well as, the third dimension of food, they need to be considered as connected problems. And for Pakistan's case, there are two key things I want to highlight. One is that it's really important to identify and fill critical knowledge gaps. The more I've studied this problem, the more I've realized that how little is known, which can, which is, I think, which is needed to better inform policy, better inform design. And what is known, there are significant gaps. So I just illustrated that example to you in our little project that we did, where we were trying to quantify the energy use in agriculture. So some of these issues really need to be addressed. And secondly, once we build our knowledge of how the water and energy systems are interacting, that knowledge really should be used to devise strategies and inform decisions. So whether we are informing decisions for funding hydropower projects, how are the economics of the project going to be affected if the flows are going to be significantly different? How much energy can actually be generated? So it's good to have large capacity, but if there's not enough flow, we're not going to get the expected energy generation. So how are we accounting for that? How is that certainly accounted for in the net present value calculations, or in the return on investment calculations, or on whatever ROIs or whatever other metrics that are being used? Is that uncertainty adequately reflected? And then similarly, how can we harness the full portfolio and not only focus on the large systems, but also on the small systems to perhaps address some of these water energy interconnections that are intimately connected in the economy of the country? So with this, I will end, and happy to take questions.
Thank you so much, Dr. Siddiqi. This was absolutely amazing to just sit here and learn from you. You're very right. Even I consider myself a little knowledgeable, considering I'm doing a PhD, and I had absolutely no idea about all these things that you mentioned. So thank you so very much. We would start the question answer session, and I'd like to start with a question that I had.
Okay.
You mentioned a temperature increase would relate to a decrease in the output that we have in water energy nexus. Could you maybe shed some more light about how this climate change, that considering what we know about how severely climate change is about to impact Pakistan, what do you anticipate in terms of generation and the water energy nexus in that aspect?
No, that's a great question. So a number of research groups have actually looked at this issue of curtailment. Curtailment meaning that, where power production has to be reduced from existing power plants because of, various constraints. And so a number of research groups have looked at this issue of curtailment in power generation because of thermal loading, and basically where the issue is that because of climate change, it is expected that the average temperature will rise, and there can be intense or sort of severe events where there are a few days of very high temperatures, which are called heat waves and so on and so forth. And in those types of situations where the temperature may spike and may stay at a very high levels for several days at a time, what would that do to power generation? Again, because as I said, the cooling processes become inefficient, and therefore, one, you can't generate the same amount of power as you would otherwise if you had colder water to begin with. Secondly, because of environmental regulations, the power plants have to do curtailment. So because of these two constraints, a number of research studies have looked at global implications where they have actually quantified what the impact on power generation can be. And globally, the expectation is that it may reduce power generation maybe in single digits, 7%, 2%, things of that sort globally. But regionally, the impacts could be very severe depending on where exactly the power plant is located, where exactly, the heat wave occurs, and what exactly might be the flow in that particular region, because ultimately, each power plant is operating on some kind of, it's withdrawing water from some kind of water body, and what really matters is what is the status of that particular water body, not of the rest of the world. So really to get that regional understanding, which ultimately is of interest beyond just global issues, what that requires is, regional studies. I am not aware of any recent work that has been done looking at it, particularly for the case of Pakistan, but it is something that should be looked at. How significant or how important that could be, I think it could be significant if, as I said, in case of heat waves, what you get is sort of a double whammy, right? You get very high temperatures, which can affect your power generation. And you also get high demands because of those high temperatures where people want to draw more electricity, they want to run their air conditioners, they want to run all kinds of cooling. So now you have a system or situation where you can't generate enough power and there's more demand for that power simultaneously. So your system gets really stressed. And this is something that really needs to be, I think, looked at and studied in more detail.
Thank you. We have a question from Nida Rahim, and she's asking, what policy change would you suggest to the government of Pakistan so that they can better overcome this issue?
Right. So one policy, well, I wouldn't necessarily call it change, but it's a recommendation, which is, what I've already highlighted here, that they really should be focusing on energy generation. Basically, how much energy can a project or system be expected to generate, and what is the robustness of their overall system. So if we put all of our eggs in one basket, then if something happens, to certain types of flows or a certain channel, then essentially all of your systems are going to be equally affected, versus if you sort of distribute your options and you sort of diversify your risks. Now, it's often easier said than done, right? We only have the Indus stem. We don't have other major rivers that are flowing through the system. So I totally understand that some of the large, projects are in a particular region and that's it. I totally get all of that. But I think keeping this mindset is still important. There are opportunities for diversification for smaller projects, let's say. Well, number one. And then number two, going back to the point that I've elaborated several times, they really should be focusing on the distribution. So looking at the probability distribution of the energy generation curve, not looking at fixed numbers that this is a 5,000 megawatt or 3,000 megawatt plant. That is not going to be the end of the story. It sometimes creates expectations that are then not later fulfilled, and it can create economic impacts as well as impacts on the supply as a whole. So really, they need to take a more sophisticated look as hydropower plants are being planned. That will they really deliver the value? Will the cost be offset by the future revenues that are expected? Will the future revenues change if the flow is significantly altered? Is anybody asking that question? I don't know. People should be asking that question.
Sadia, would you have any questions as well?
Yes, I do have a question. Thank you, Dr. Siddiqi. That was extremely, extremely informative. And you talked about groundwater pumping, and you gave the example of Punjab. So Balochistan, there's 16,000 diesel powered. And I think out of 1,600 megawatts demand in Balochistan, 800, 900 megawatts is because of these water pumps, which they're using for orchard farming. Now, the government is considering converting them to solar power pumps. But as you said, that can actually have negative effects as well, that can lead to reduce water table or reduce water flow. So, I mean, what do you suggest? Like, what are the technologies that the government should consider, or those multilateral agencies that are going to be supporting government in this project? What question they should be asking, and what technology they should be considering, so that we don't lead to a situation, because India has had this situation where water table has actually gone down because of solar pumping.
That's right. So you're absolutely right. Balochistan's case is very extreme, and there are a number of some good studies that have looked at that issue. The issue of solar water pumping, as I mentioned earlier, is certainly very attractive in terms of clean energy and so forth. The biggest issue that anybody and everybody needs to ask who are thinking about the planning and funding of these systems is that, how are these systems going to be regulated? That is the only question to ask. Now, in terms of, are there technologies? Yes, there are some, technologies that can be installed on those pumps that will allow one to either monitor them. In some cases, I know some people have been trying to even institute, some types of controls where the pump will only operate for X number of hours, this, that, or the other. There are many different approaches to which you can technologically institute, regulatory sort of mechanisms and devices to have some level of control or accountability, or at least visibility of what exactly is happening with the pumping situation. That is just very important. So it's just a matter of, what a particular devices that one may find, cost effective and feasible to use. But certainly some of these do exist, and it needs to be sort of really looked at. That solar water pumping is great, but the biggest question is that, can it be done responsibly? So the real focus should be on how do we do this responsibly? And the responsibility question goes beyond just technical measures. Really, that's how I feel it, right? I mean, we can bring in any kind of technical solution, but that technical solution can always, there's a workaround, and where if that technical solution is not viewed as helpful or productive by the end user, the end users will find ways around to either sort of limit the device, or even and so on, and work around other ways. So what is really important is also, I think, sort of public awareness, as well as incentives and mechanisms that can limit the need for overpumping. And it's easier said than done, but I do feel that a lot of awareness, as well as which is of course comes through education, but also creating incentives that might just lead end users to not overpump. Rather than only going for technical solutions. What those incentives might be, that's for, I guess, another discussion and another talk, but that's overall what I would say. That for solar water pumping, what is really needed is responsibility, transparency of what the level of pumping would be, and some level of regulation and control. And that regulation and control should be through a mix of not just technology, but also behavioral changes and incentives. Mm-hmm.
Thank you so much, Dr. Siddiqi. We have one very relevant question to our audiences, and that question is from Namira Hamid. She is the co-founder of Women in Energy, and she's asking, Dr. Siddiqi, would you also please share your career trajectory and some advice for younger professionals who are entering in this field?
Sure. So, my career trajectory has been anything but linear. And now as I sort of look back, I observe that, it's more common than not. If you ask many people, they will, I think, give you similar answers that their trajectory or their career path took them to places that they had never expected that they would, end up in. But it's been great. My own training was in mechanical engineering and aerospace systems, and I was very interested in aerospace systems, and I continue to work in that area. But I got interested in sort of research after working as an engineer for a few years, and I realized that I get curious about a lot of different things. And if you're working in a company, there are only a few things that you can actually work on. And it was really my own interests that then got me more interested in research. So I came back to MIT and got a PhD. I just wanted to, work on bigger issues, different issues, and so on and so forth. So I focused on systems analysis. So my initial training was actually in controls. Both bachelor's and master's was in systems controls, so which is very low level, very device oriented, very sort of low level issues. But from PhD, I looked at systems modeling and analysis, and I think because of the nature of systems modeling and analysis, where you're looking at large scale systems, it's a very natural transition to get interested in policy, in my view. And that is what happened to me. I got really interested in policy, where I was interested in, and I realized that if you really want to make change in the world, it's not going to come through technical solutions alone. Technology is only one small piece, actually, in the bigger puzzle of, development, of improving people's lives, of improving our country, improving our planet, right? There's a lot more that goes into beyond just inventing new technologies or improving them. And that's what got interested me in policy, where if you can come up with good rules of the game, and if you can come up with a good set of incentives and good set of rules, you can really institute a large change at a large scale. In terms of what I do today, after I got my PhD, I sort of remained in academia, remained in research. I really enjoy it a lot. I find it extremely fulfilling. So for people who are considering different options, my advice is that be open and experiment. It is often that until you do something, you will realize what it is that you like about it or what it is that you want to change. So I actually worked as an engineer for a few years, and I realized that I really want to look at other bigger problems, and then I got into research, and I find that very meaningful. So everybody has their own sort of preferences, their own ambitions, but be ready to experiment and change. If somebody had told me that I would be in academia and I would be a research scientist 20 years ago, I would have said no way, absolutely not. I just wanted to be out in the field and just be doing things, and that's what I enjoyed. But it's only through experience that you discover new things that you enjoy or new things that you like. So be ready to experiment and really have an open mind, and be ready to take opportunities that may come your way. Don't limit yourself to a prescribed check boxes list that one needs to go through. And in terms of, one last piece of advice, I would say that I think it's really important for people to think about big problems and work on issues that go beyond, simple profit maximization and simple, sort of, bottom line related questions. I think it's really important, and I'm very hopeful, and I always get inspired when I talk to the new engineers and the younger people and the students, that they really have that sense of ambition and inspiration to do things better, make our world a better place, and that's the advice I would give to everybody. That's what we should all be aspiring towards.
Thank you so much, Dr. Siddiqi. We're going a little over time, so I'd like to wrap up. Thank you so much for your precious time. I'd like to give a special shout out to Dr. Sarah Jordan for connecting everybody in this webinar. Thank you for Women in Energy Pakistan and Sadia and Namira, who help us become more knowledgeable in all these different sectors that pertain to energy and gender as well. For everyone who missed out on the starting part of the webinar is stored at our Facebook page as a live series. You could go to facebook.com/Women Engineers Pakistan. And you would find this webinar and the previous ones all there. Feel free to go and learn and shout out if you have any questions for us, and we'll try to get those to our speakers as well. Once again, thank you so much to Dr. Siddiqi and to Sadia. I hope all the audience learned as much as I did, and I will see you next month. All right.
Thank you.
Thank you.
Take care. Bye-bye.